So in the next homework assignment, we're going to be using the mean value theorem. And what we want to do before we jump into proving the mean value theorem or using the mean value theorem is just to understand the concept of the mean value theorem. The conceptual understanding of what the theorem is telling us is probably the most important thing. And what we want to do before we try to understand the mean value theorem is step back to the previous homework assignment and look at Rolle's theorem. Look at Rolle's theorem and what Rolle's theorem was telling us. So Rolle's theorem, remember, said that we wanted to have a function that was continuous, so no discontinuities, continuous over a closed interval, and differentiable. The derivatives needed to exist over an open interval. And the claim was that if f of a equals f of b, that there had to be some input c on the open interval from a to b such that the derivative at c was equal to 0. And so what we really want to understand is conceptually what Rolle's theorem is telling us. And Rolle's theorem really is telling us, hey, if f of a is equal to f of b, then the slope of the secant line through those 2 points, which you can calculate like this. So the average, calculating the average rate of change, the output 2 minus output 1 over input 2 minus input 1. That's the slope of the secant line through 2 points, which we've used extensively this semester. So what Rolle's theorem is really saying, hey, if f of a equals f of b, then this numerator on the average rate of change calculation is going to be 0. So Rolle's theorem really says, hey, suppose you have f of a equaling f of b. Then when you calculate the slope of the secant line between those 2 points, the slope of the secant line is going to be 0. And Rolle's theorem says if the slope of the secant line is 0 and you're working with a continuous function on a closed interval that's differentiable over an open interval, Rolle's theorem is saying, hey, if the secant line slope is 0, there's going to be some value c between inputs a and b that has a tangent line slope of 0 as well. And this is what we looked at in the previous homework assignment. So Rolle's theorem, the gist of it is that if the average rate of change is 0, then there must be some place on that interval from a to b at which the instantaneous rate of change is also 0. And then we want to ask the question, what we want to do is to get to the mean value theorem, we want to ask the question, what happens if f of a isn't the same as f of b? Well, if f of a and b are not the same, that's going to be something like this. Suppose f of a isn't equal to f of b. That means either f of b is greater than or less than f of a. So we either, on this picture, would get a line tilting up if f of b is greater than f of a, or perhaps a line tilting down if f of b is less than f of a. So kind of without loss of generality, let's suppose f of a is actually bigger than f of a. So if f of b is greater than f of a, we could take each of these pictures then and kind of tilt them up in such a way that still leaves don't want to delete the whole picture, just the little scrub pieces on it. So if f of b is greater than f of a, we can tilt it to the right so that the slope of the secant line is now positive, and we keep the value of c corresponding to this point right here. We keep it between a and b on the horizontal axis. So I could do the same thing with this. I could say, hey, if f of b is greater than f of a, let's tilt that up so that we represent f of b being greater than f of a. So the only thing we change on Rolle's theorem, the idea is, suppose the only thing we change on Rolle's theorem is criteria 3 that f of a had to equal f of b. What would that change about the claim that you would make? Well, the claim that you would make is that instead of the average rate of change here being 0, because the slope of the secant line is no longer 0, in fact, it's a positive number. If f of b is greater than f of a, you can see the slopes of the secant lines are positive. So the only thing that would change in the claim would be, hey, if the average rate of change, the slope of the secant line, isn't equal to 0, there must be, I shouldn't really say that. It could still be 0. But the claim would be that the slope of the secant line has to equal the derivative evaluated at c for some c on the interval. So say that one more time. If f of a isn't equal to f of b, or we allow for the possibility, we don't require that f of a equal f of b, Rolle's theorem would change in the sense that we would be making the claim that the slope of the secant line right here, or the slope of the secant line right here, or the slope of the secant line right here, we would be making the claim that there must be some input value c between a and b, so that the slope of the tangent line right here matches the slope of the secant line, so that the slope of the tangent line is the same as the slope of the secant line. Or in other words, the average rate of change is equal to the instantaneous rate of change, and they may not be 0. So that's what the mean value theorem does. So the mean value theorem at its core has the same first two criteria that Rolle's theorem did. The mean value theorem makes the claim that, hey, let's suppose we have a continuous function, so f of x is continuous on a closed interval and differentiable on the corresponding open interval. But we don't require f of a to equal f of b. We say, well, it could, but it doesn't have to. So the claim is that there must be an input value c on the open interval from a to b at which the derivative matches the average rate of change. So remember, the derivative is the slope of the tangent line, and the average rate of change is the slope of the secant line through 2 points. So the claim that the mean value theorem makes is that the instantaneous rate of change, the slope of the tangent line, will match at least once the slope of the secant line. So essence of it is average rate of change will match instantaneous rate of change at least once on the interval you're interested in. And you can kind of think about this conceptually. So suppose you were thinking about taking a car trip. So let's say we plot our speed over time. So let's say we are driving our car between 3 p.m. and 4 p.m. on a road trip from Ellensburg to La Grande, Oregon. So we were working over the closed time interval from 3 to 4. And let's suppose that at no point during our trip do we stop. We're just driving on the freeway. Nothing stops us. And over that closed time interval, our speed is going to fluctuate. We won't always be going exactly the same speed. So on that trip, there will, if we're working over a closed time interval with a continuous function, the extreme value theorem says that there must be a lowest speed that you were at and a highest speed that you were at over that time interval. So let's suppose the fastest you went was 80. So over here on the speed axis we have an 80, and the slowest you went was, let's say, 40. Well, your time's been fluctuating over the whole trip. So you are going to have an average speed. Let's suppose your average speed was 70 miles per hour. There was your average. So the mean value theorem, what the mean value theorem really is saying is that if your average speed was 70, there must be some point, at least one point during the trip when you were doing exactly 70 miles per hour. And that can happen more than one time over that time interval. So the big claim that the mean value theorem is conceptually making is that, hey, you have an average speed of 70. Well, you weren't doing 70 at all times. Your speed was fluctuating. Your low speed of 40 right here, you got stuck behind a semi-truck. You sped all the way up to 80 miles per hour, and then you saw a cop and you hit the brake and you slowed down. So the mean value theorem just identifies that as long as you have a continuous differentiable function over a time interval, your average speed this flat line here, has to match your instantaneous speed at least once, and it may happen lots of times. And if you think about it, it makes sense, because if you're going between a low speed and a high speed, so let's say you're going from 45 miles per hour here up to 80 miles per hour here, can you get from 45 to 80 without doing 70? Well, the only way to get from 45 to 80 without doing 70 would be to jump over 70 miles per hour. And if you jumped over it, you would have a discontinuity. You would violate the claim that you have a continuous function. So at the core of it, bottom line and summary, mean value theorem just says if you have an average speed or an average rate of change, there must have been some point, as long as you're working with a continuous differentiable function, there must be some point at which, at least one point at which, your instantaneous speed or instantaneous rate of change is the same as your average.